So now we are going to have some problems which can be addressed using the concept of stationary distribution of a Markov chain. So by the time stationary distribution of a Markov chain uh, with the transition probability matrix P, we mean that vector probability distribution vector such that pi into P is equal to pi. P is the transition probability matrix and pi is a vector. Then in terms of linear algebra, we term this kind of vector pi as left eigenvalue of P. And there is another result. If we have the value of P, transition probability matrix for a homogeneous regular finite state Markov chain. So I mentioned the terms again. Uh, regular regular means all the values of P are positive. Then regular homogeneous, which means the transition probability from nth stage to n plus 1 stage is independent of the value of n. It is homogeneous. Then the next term is finite state. So S is finite. Uh, and the Markov chain. If a Markov chain has all these three properties, then we have a result. It says that limit n tends to infinity p raised dn is equal to q, where q is a matrix whose rows are identically equal to the stationary distribution pi. So that's the method by which we can find the value of p raised dn as n tends to infinity. Or in other words, as n tends to infinity, p raised dn gives the stationary distribution in each row, and that row is identically equal to the steady state um, distribution, steady state distribution or stationary distribution pi. So let us illustrate this concept using an example. So consider a model in which the transition probability matrix P is a square matrix zero point 0.5, zero point 0.5, 0.1, 0.9. So that's the value of P. And we are just going to check or find the uh, steady or stationary transition probability matrix or steady stationary probability. So it is pi into P is equal to pi. So for simplicity, we just take pi as say pi naught pi 1 as a vector. Uh, so it is uh, pi naught pi 1 into zero point 0.5, zero point 0.5, zero point 1, zero point 0.9 is equal to uh, pi naught pi 1. That means zero point 0.5 pi naught plus zero point 0.1 pi 1 is equal to pi naught, and 0.5 pi naught plus 0.9 pi 1 is equal to pi 1. So here we get two equations, uh, and we have to solve these two equations simultaneously. So for that, we rewrite it as a system of homogeneous equation. This pi naught is shifted to here, and it gives zero point 0.5 minus 1, that is minus 0.5 pi naught plus 0.1 pi 1 is equal to 0. And if this pi 1 is shifted here, it is 0.5 pi naught uh, minus 0.1 pi 1 is equal to 0. So here actually what we got is two equations in two unknowns, but practically there is only one equation because the second one is obtained by multiplying the first one with say a minus 1. So we have one equation in two unknowns. So what we have here is from the first equation we can have a relationship between pi naught and pi 1 like uh, minus 5 pi naught plus pi 1 is equal to 0 or pi 1 is equal to 5 pi naught. So the eigenvectors are given by pi is equal to something like pi naught and pi 1 divided by 5. But there are infinitely many. Okay, the second term can be written in terms of pi naught. So pi 1 is equal to okay, let us write like this. Um, Pi is given by the first term is pi naught and the second term is pi naught uh, 5 pi naught. Now since this stationary distribution is a probability density function, actually there are infinitely many eigenvalues. Any linear multiple of this pi naught is an eigenvector to the transition probability matrix P. But since it is a probability density function, since pi is a probability vector, we have pi naught plus pi 1 is equal to 1, or in other words pi naught plus 5 pi naught is equal to 1, which means pi naught is equal to 1 by 6. So we can have the value of pi as 1 by 6, 5 by 6. So that's the steady state probability density function of our Markov chain with the transition probability matrix P. So what's the meaning of this pi? In long run, the system is in state 1 with probability 1 by 6 and system is in state 2 with probability 5 by 6. So that's the implication of steady state or stationary distribution. Now let's have one more problem. Let's consider um, the transition probability matrix P is equal to 0, 1, 1 by 2 or 0.5, 0.5. Now find the steady state distribution of this particular matrix, which is given by pi into P is equal to pi, which gives pi naught pi 1 into 0, 1, 0.5, 0.5 is equal to pi naught pi 1. That means uh, 0 into pi naught uh, plus pi 1 into 0.5 is equal to pi naught, and second one pi naught plus 0.5 pi 1 is equal to pi 1. So from this two equations we can have pi naught minus 0.5 pi 1 is equal to 0, and from the second one, pi naught minus 0.5 pi 1 is equal to 0. So these two are the same equation, and this gives pi naught is equal to 0.5 pi 1. So our eigenvector pi is of the form pi naught, and second time pi 1 is pi naught divided by 0.5, or it is 2 times pi naught, or from here pi 1 is equal to from here pi 1 is equal to pi naught divided by 0.5, that is 1 by 2, that is 2 pi naught. So that is our eigen value of our transition probability matrix. And since it is a probability matrix, pi naught plus 2 pi naught is equal to 1, which gives pi naught is equal to 3 pi naught is equal to 1, or pi naught is equal to 1 by 3. So the stationary distribution is pi naught, that is 1 by 3, then 2 pi naught, that is 2 by 3. So this is our uh, transition stationary probability distribution vector. So this is the concept of stationary probability distribution vector of a Markov. Now let us have another Markov chain with the transition probability matrix P equal to transition probability matrix uh, P equal to P small p small q and p with the values p and q are in between 0 and 1, 0 less than p less than 1, and p plus q is equal to 1. So here p plus q is equal to 1, q plus p is equal to 1, and the value of p is in between 0 and 1. Then obviously the value of q is also in between p and 1, and it is not equal, p is not equal to 0, therefore q is also not equal to 0. So obviously we can make things like p not equal to 0, q not equal to 0, and the value of q is in between uh, 0 and 1. All these things can be uh, reduced from the given conditions. So since the value of p and q are not equal to 0, it is a regular matrix, and it has only a finite number of states, 1 and 2, and uh, the initial probability distribution is also given p naught as alpha 1 minus alpha, where this alpha is in between 0 and 1, and 1 minus alpha is the probability that the system is in state 2. And the questions which we have to answer is first one, find the probability distribution after probability distribution after one step, then after two step, then see after infinite step. So it is given that x naught take value 1 with the probability alpha, and 2 with the probability 1 minus alpha, and we have to find what about find the probability that x2 or x1 take the value 1 with how much probability, and x2 with how much probability. So the transition probability matrix is given. So if we calculate p naught into p, that will give the probability matrix after one step. So P is the one step transition probability matrix, and P naught is the initial the distribution. Then P naught into P will give the probability distribution after one step. So that is given by alpha 1 minus alpha into P Q Q P. Just multiply. This will give alpha P plus 1 minus alpha into Q, the first component. The second one is alpha Q, then plus 1 minus alpha into P. 1 minus alpha into P is equal to alpha P minus alpha Q plus uh, Q. So that's the only simplification which we can have. So here it is alpha into P minus Q uh, plus 1 into Q, that is plus Q. Then here it is alpha Q minus alpha P, so it is alpha into Q minus P uh, plus 1 into P, that is P. This is the probability density function or probability distribution after one step. And if we sum these two components, P alpha into P minus Q plus Q alpha into Q minus P plus P, if we add these two times, what we get is P plus Q is equal to 1. So that's the property of probability distribution. So that is how we can check whether our answer is or it's a method to check the correctness of our answer. Anyway, to find the steady state probability after two steps, we multiply the initial probability distribution with the two steps transition probability matrix, and the value of two-step transition probability matrix is nothing but p square by Chapman-Kolmogorov equation, and p square is equal to p q q p the square, so that is equal to p q q p into p q q p, which is in fact equal to here the first time p into p square, p into p square, q into q q square, then p into q pq, then q into p qp, so pq plus qp is equal to 2 pq, then q into pqp, p into q pq, so it's again 2 pq, then here it is q square plus p square, so it is p square plus q square. So that's the two-step transition probability matrix. Then we multiply p naught, that is alpha 1 minus alpha, the initial distribution of probabilities, with the with the two-step transition matrix. Then we have the required probability distribution after two steps. So this product is equal to alpha into p square plus q square plus 2pq into 1 minus alpha. That's the first component. Then the second component is alpha into 2pq, that is 2 alpha pq, then plus 1 minus alpha into p square plus q square. So here I think not much simplification is possible here. We can make some simplification by okay, we can take something by taking alpha as a common factor here, and it is alpha p square plus alpha square q square. So it is we sum up the terms of alpha. It is p square plus q square minus 2pq. Then what remains here is plus 2pq. And here also, if we sum up the terms of alpha, it is alpha minus alpha into p square plus q square. So it is minus of p square plus q square, and here we have a plus 2 alpha pq, so it is minus 2 pq. They are all minus. Then the constant term here is 1 into p square plus q square, so it is plus p square plus q square. So this is equal to alpha into p minus q the whole square plus 2pq, and the second component is here is p square plus q square. Sorry, it is here we have an alpha. So it is minus alpha into p minus q the whole square plus p square plus q square. So this is the probability distribution after two steps. Now, to find the probability distribution after infinite number of steps, what we are actually looking for is the stationary distribution. Is the distribution after infinite number of steps, and that stationary distribution is given by the Leftigian vector, which is nothing but pi into p is equal to pi. We take pi is equal to pi naught pi 1, and pi naught pi 1 into p q q p is equal to pi naught pi 1. That is here p into pi naught plus q into pi 1 is equal to pi naught, and the second equation is q into pi naught plus p into pi 1 is equal to pi 1. So if we write them as a homogeneous system of equations, then what we have uh, is transform this into the left hand side, to transform this pi naught into the left hand side, then what we get is 1 minus p into pi naught plus q into pi 1 is equal to 0. 1 minus p is nothing but q, so this equation is q pi naught plus pi 1 is equal to 0. So actually q pi naught plus q pi 1 is equal to 0. So q into pi naught plus pi 1 is equal to 0. That means pi naught plus pi 1 is equal to 0. Similarly, we can rewrite the second equation, that is q pi naught plus p minus 1 q pi naught plus p minus 1 into pi 1 is equal to 0. That is here also we have it is p minus 1 minus p. It is phi naught is shifted here, so this minus 1. So what happens here is it is uh, p minus p minus 1 is uh, negative q, or 1 minus p is q, so it is minus q. So here we have a negative sign, and in a similar way here also we have uh, q into pi naught minus q pi 1 is equal to 0, which is q pi naught is equal to q pi 1, or pi naught is equal to pi 1. So we don't need to solve these two equations. Obviously those two equations will give the same set of equations, or the linear multiple of first equation as the second one. So uh, anyhow, the eigenvector is pi naught pi naught, because pi 1 is equal to pi naught. This is our eigenvector, and since it is a probability distribution, pi naught plus pi naught is equal to 1. That means pi naught is equal to 1 by 2. So our eigenvector pi, or the stationary distribution pi, is nothing but 1 by 2, 1 by 2. So after infinite number of steps, the stationary distribution is 1 by 2, 1 by 2, which means the probability to be in state 1 and the probability to be in state 2 are the same. So that's a stationary distribution of our Markov chain. So I think this is enough problems for today, and in our next class also we will cover a number of problems which can be related to steady state probabilities and the transition probability metrics, and the probability after infinite steps, etc. Uh, so for the time being, I'm stopping here, and uh, I recommend you to go through a number of problems which can be solved using the Chapman-Kolmogorov theorem. So that is the most important result in this chapter, Chapman-Kolmogorov theorem. We don't need the proof of this particular result, but the statement is important. In exam point of view, the statement may be come as a question. You have to state Chapman Kolmogorov theorem, so that's important, and the application is very much important. We have to go through a number of problems which use Chapman-Kolmogorov theorem. Okay, so for the time being, thank you. We will meet again with a number of other problems.